What happened? We got stuck at 10. What happened to your friends? Don't you want to continue? I'll keep this short, maybe 10-15 minutes, and then we'll wind up today. Okay. Let's wait for one more minute. All right. So can you see my screen? Okay. Don't worry. Whoever are there, let's just continue for some time. You can see the screen. Can somebody tell me? Can you see my screen?
Yes, sir. Yes, sir.
Okay. Okay. Perfect. So you already got an idea that as the size decreases, the surface area increases. Now let's understand this even more. Let me say, wait, let me go to full screen. Let me take a pen. Okay, now suppose I have a cube of side A. Okay, of side A, then the surface area is 6A square, right? We already talked about it. Now let's cut this up. Okay, sorry, let's cut this up into two parts. Okay, that means we separate it out. We are not changing any volume. Volume is still the same. Okay, but we are just cutting through and making it into two pieces. That means what I'm trying to say, if I try to draw that again, this is one and this is the second one. We made it into two blocks. Okay, so this was the original A. Okay, this is also A. So now what will happen? This side and the one behind this, right, and the one that is behind this, these are new surfaces that came up that was not there in the previous one here, right? So how much will be the surface area now for this one? How much will be the surface area now? Say for this one it will be, we have four sides now. See, this has become A, but this is now A by 2, right? This part is A by 2. Okay, this pen is not writing properly. Okay, this part is A by 2, this one. So ultimately what is happening, this surface area of A and A, that means A square, and the other one on this side A square, so 2A square surface area has increased, right, because of this surface and the other surface hidden here. So what will happen now, the surface area, previously it was 6A square, now it will increase by, sorry, 2. Let me I don't know, this is 2A square. So you are getting 8a square. Okay, that means once you break it up into two parts, you're already increasing the surface area. Okay, and if we continue that way, that means we break it up even more this way also, this way also. Okay, you can, that's what we are doing when we are breaking it up. We are not increasing the volume. Volume is still here. It is the volume is a cube, right? No matter what, it is always here also. It is a cube. If you break it further, it will be a cube. So the volume is not changing, but the surface area will keep on increasing. Okay, and if you take these small blocks to nanometer sizes, you will be surprised to know that the surface area might increase even 1000 to 10,000 times on the same volume. Okay, so uh, let me use the eraser. Where is there an eraser here? Eraser. All right, let me erase. So now thinking about pharmaceutical now, because all of you are from pharmacy. Now you are all are experts in tablet making, right? Can somebody let me just tell you that I make a, let me go back to my pen. So we need the pen, and let me make a tablet. This is a tablet, okay? Please forgive my drawing. And this is maybe another tablet, okay? Small ones, big ones. So why do you make it bigger? Because you have to put more medicine. The medicine is added, right, on the tablet, which is normally calcium sulfate as far as I know, but you will know more than me on this. But one may be small, one may be big, and sometimes it's so big. So I remember my mother, unfortunately, she left me last November. She used to complain about the big tablets like this. It's difficult to swallow. Okay? Now, but then you cannot help it because you have to put in more medicine here. That's why you need a bigger size. Now think about it. So suppose this small one itself, it has a surface area of x centimeter square. Now let me magnify this now. Okay, I am magnifying this. Let me draw it bigger. Okay, so let's say this is x centimeter square. Now if we'll do some more calculations in the next week, if I simply do some what we call as nano structuring on the top using the same material, okay, that means you are using uh, say suppose you are using, I don't know, calcium sulfate maybe. So same calcium sulfate, we can, what we can do is we can put in a small layer of nanoparticles of the same material on top. We'll do some small calculations as to see how it is. So suppose we are putting some nanoparticles on top of the tablet. Immediately the possibility of the surface area going to 100x on the same size. The tablet size is still this one, but now you can put in 100 times more medicine on your tablet. Okay, so my mother will be happy to swallow that one. So that type of possibility is there, that because you can play around with the surface area. Okay, we'll do some calculations in the next class, so to get an actual idea of how this happens. So I told you before that I think yesterday we mentioned that we are going to have the first sessional exam from fifth. So there we might do some small calculations like this. I will solve some for you, and you will see then the amount of surface area that can happen. Now let me let us try a small problem today. Okay, today in the sense you try it out. I'm not saying or that you will be 100% correct, but let us try a small problem which might be interesting. Where is the eraser? Just a minute. Eraser. Eraser. Okay. Let's try this. I'm not giving it as an assignment. I just want you to try this. Okay. Uh, we can discuss it again in the next class. That means the next class is on next Tuesday. Okay. In the meantime, there's enough time for you. Let us try a problem like this. Say you have. Just a minute. Let me get my pen back. Okay. You have to take it down. Okay. If you have a pen and paper with you. So or you can take a snapshot of this. It's easy for you. Say let me first tell you the problem. Let's say we have a tablet. We have a tablet like this, a circular tablet with a radius of r, okay, and a height of h. Okay. Now we take some nanoparticles of the same material, okay, and suppose the nanoparticles diameter is r dash. Okay. Now what you have to find out is that if we coat the tablet on all sides with this nanoparticle, that means we put one layer of this nanoparticle on all sides of the tablet, something like this. If I have to draw it again, we have these nanoparticles sitting tightly, but only one single layer, which may not be possible physically to exactly get this, but try to understand this, that this is a mathematical one. We will cover the whole tablet on all sides with a particle of this radius. Okay. So now if I give you some numbers, say suppose the typical radius, let's just say the radius of your tablet is how much? Let's make it simple. We say it is 1 centimeter. I know it will be too big maybe, no? But anyway, let's say it is 1 centimeter. The height of the tablet is 2 millimeter. Now you have to be very careful of the units, okay? One is given in centimeter, one is given in millimeter. And r dash, that means the diameter of the spherical nanoparticle is suppose, we give it as suppose 10 nanometer. Now this is nanometer, okay? You have to be careful with the units. So if these are the numbers given, by how much will the surface area, says if I say this is surface area 1 S1 and this is surface area S2, then you have to find out S2 is equal to how much of S1. That means how much is X. Okay, you get this? By how many times will the surface area increase if we coat your tablet with nanoparticles? Now, just to give you a hint, if I draw the side view of the tablet, okay, if I draw the side view of the tablet, this is the tablet, directly the side view, then actually if you look at the particles will be sitting something like this. That means, this, if you look at this now, actually these are spherical particles, but they're touching each other. So effectively, only half of the sphere here, the half of the sphere here will be available for the medicine to sit on. The surface area will be only half of the sphere will be available, the other half will be below. Okay, so it will actually finally look something like this. Okay. Hope you understood the problem. Any doubts on this one? You can ask me. Let's try to solve this. Not now. You solve this. We will discuss this in the next class next week. Any doubts? Is this clear to everyone? The problem? Yes or no? Somebody?
Yes, sir, it's clear.
Very good. So any doubts we can always discuss on the WhatsApp group, okay? So you don't have to wait for a next class to ask me any doubts if you have, okay? You put it up and I always keep 10 p.m. to midnight. I keep it for my students. But the problem of taking phone calls is that, you have to dedicate full time to one student if you talk on the phone calls. So I have so many groups of students. So I discuss with everyone during that time. So if any question comes up to your mind, you immediately write. I'm not saying you have to write at 10 o'clock, but I will reply after 10. Okay, between 10 to 12, I'll give you the replies for your queries and doubts. So try this out. I will also solve this. I'm just giving it on the spot, so I also don't know the answer. So let me also solve this, and then we will discuss in the next class. Let me skip all this. Let me see if something interesting is there. All right, now I'll pick this up in the next class, but last to give you the small definition so that we can discuss again later is that when you talk about nanomaterials, I told you, no, that one dimension has to be less than 100 nanometers as per the definition. Now we have certain types of nanomaterials which we call as zero dimensional, one dimensional, two dimensional, and three dimensional. Okay, four different types of nanomaterials. So zero dimensional means that in all three dimensions, the quantum confinement, or that means the electrons are not allowed to move. Okay, I'll again have to explain that. I will put in some physics later. I don't want to frighten you with a lot of physics initially, but think about the situation that the electrons are in a constant random motion. Okay, and this motion can happen in three dimensions. Now if we restrict the motion in all the three dimensions, that means the electrons are not moving around, they're stable, they're fixed. That means they're not moving around from maybe one atom to the other in all the three dimensions, then we called it as a zero dimensional material. Okay, that means the quantum confinement is happening in all the three dimensions. Now if it is happens in the confinement happens in two dimensions, that means the electron is not allowed to move in two dimensions, but it can freely move in one dimension, then we call it as a one dimensional material. And if we can restrict the electron in one dimension and it is allowed to move freely in two dimensions, then it is a two-dimensional material. So, and if the electrons are free to move in all the three dimensions, we call it as a three-dimensional material. Now, a typical example of a zero-dimensional material is a quantum dot. Okay, I'm sure you've heard this term quantum dot. These are basically nanoparticles. Okay, when the nanoparticle material is a semiconductor, we call it as a quantum dot. Okay, so it's just a nanoparticle which is extremely small, okay, and it's mostly spherical in shape. Then we say that is a zero-dimensional material. Now think about a nanorod. I showed you some images of some rod-like structures. I remember I showed you this. I made myself. Those are moving in one direction. Okay, the rod is long in one dimension. The other two dimensions are smaller. So there, the electrons are allowed to move in one dimension, and that is a typical of a one-dimensional material. Now, if you make a thin film, that's now I showed you the tablet, okay, where we'll put the nanoparticles. That means that will become a thin film once we put those nanoparticles, because the individual nanoparticles are zero dimensional. But the moment we put them on the tablet surface, we make a small film of it. We call it as a thin film. Then it becomes a two-dimensional material. So the original zero-dimensional, once we lay them out together, we become a two-dimensional nanomaterial. Okay. And the three-dimensional ones are basically two-dimensional ones from where another dimension grows. So that I'll explain later with some figures. They are called as superlattices and heterostructures. These are the examples. Okay. So I don't want to put too much on your head at the moment. What we will do is we will go slowly initially on the topics, and then we will pick up, we'll accelerate. Okay, then you will be able to grasp more. You see, this is something which we lack, because let me tell you a small story in 2 minutes. Uh, when I shifted to Sweden, because previously I was in Thailand, and my son, he joined me when he was 2.5 years old. So he just did 1 or 2 months of schooling here, and then he joined an international school in Thailand, in Bangkok. Okay, and then from there he landed up in an international school in Sweden. Now Thailand was sort of similar to India, the way the education is given. But when we reached Sweden, I was so worried because there are no books at home, does not bring a copy back home. I really didn't know what he was doing in school, and there's no such thing as a homework. And I was so worried. So one day I, took an appointment with the teacher, because there also it's one single teacher was teaching one class, not like here that we keep on changing the teachers subject wise. There, it's like one teacher, it teaches everything. Okay, and I went. She was a British lady, and I went and approached her, and I said, "I need to discuss something. I'm so worried." And then she said, "What happened?" I said, "I don't know what my son is doing, and he does not study at all at home. I'm so worried." And the lady smiled and she said, "Why do you want him to study at home? What is he doing in school? You sent him to school to study, right? So why does he have to go home and study?" I said, "But then how will he cope up? Because I think you're teaching too less, because I asked some mathematical problems he couldn't solve." And I told her that my case, when I was his age, I knew a lot more mathematics than he's learning now. Okay, and then what she said is that in India, I think you follow what is a very linear way of academics. That means you start at maybe nursery and you go to, this is nursery, suppose this is class 10, suppose. And she said that you go very linearly. That means whatever you're supposed to learn, you're breaking it up and you are going that way in a linear way. And what they do in Sweden is that they go at it this way. Okay, that means initially they keep the load less, so the students try to understand, grasp, and enjoy reading, not get frightened of school. Okay, they enjoy, and then when the mental capability goes high, maybe this is class 8 to class 10, they take the same jump. It's a huge jump, but they're capable. Ultimately, at class 10, both of us, or both of them, reach the same place. So I'll try to do something similar here. Okay, so initially we'll go slow so that you guys grasp the basics of the whole thing, and then finally towards the later part of the semester we will go accelerate a bit and we'll jump up the steep hill then. Okay, hope this is okay. And any doubts, please WhatsApp me in the group. Okay, and I'll try to answer in simple ways. And let's try to make this a very good learning experience. Okay, because I see a lot of possibilities also in this area as far as pharmaceuticals are concerned. And if you plan to go ahead for your masters or your PhD studies, all this might be very, very interesting and very, very exciting. Okay, so I'll stop here today. You guys explore this one if you can solve this problem. Okay, and I might put in small dose in the WhatsApp group. Dose means small parts to study. Okay, let's not burden ourselves. Small things, but whatever I put in there, do read once. Okay, or if I put a small audio clip or a video clip, do go through. Fine, and let's see how much we can transfer the knowledge from one side to the other. Fine, and I'm always open to discussions. I'm always open to hearing from you guys also. So explore videos. You'll find a lot more videos on YouTube. Go through, a lot of exciting things happening as far as nanotechnology is concerned. Okay, so I'll stop here today. I have a meeting, and you guys please give me your attendance. I'll put them in. Fine. And one of you, your name is not registered. I sent a message. Kindly check out with your mentor and see that your C includes your name. Okay. All right then. Thank you, everyone. Take care. Bye for today. Okay.
Thank you, sir.
Thank you, sir.
Okay.